Nash could show was that always exists. What do I mean by mixed any? By mixed any, I mean that players can play randomized strategy. They can say with half the probability I am going to complain, with other half probability I am not going to complain. With 1/3 probability I am going to complain, with 2/3 probability I am not going to complain. This is a mixed strategy. And then we are going to analyze the payoffs and see that does there exist an equilibrium where no player has incentive to switch their strategy. Okay, so now we are increasing the possible moves. We had these deterministic strategies, we can even play a probability distribution over these strategies. Okay, so, and then we will understand what the payoff is and all that, we will do it. But at the first, what we have done is increased possible strategies. For example, ith player can play any probability distribution on Sn. Okay, once we do this, then we are going to prove the theorem that any exists. Okay, any exists not just for zero-sum games, for games, finite games in general. That's a big theorem. We're not going to worry about it. What we are going to show is okay, and obviously this is why Nash had a beautiful mind. Okay, this is the reason why he got Nobel Prize. Okay. I think it is, so at least for this, it is just the idea of it. The proof, now especially with strong duality, is actually not very difficult. John Nash was famous because his PhD thesis was like 17 pages long, which was like the best thesis in years. Generally, the PhD thesis starts from like 60, 70 pages and goes up to 200, 300, 400 pages. So clearly the proof was not difficult. Coming up with proof, the idea was very nice, and that we will see. Okay, so remember n equal to 2, we are talking about 2-player zero-sum game. That means basically our game will be described by a matrix A. M is the number of first player strategies or size of S1. Size of S2. Okay, and Aij is the payoff. Let's say, for first player. What about the payoff for the second player? Okay, so in this case, my game is described by just a simple M cross N matrix. I am interested in that matrix, trying to find out whether there is a mixed Nash equilibrium. I will stop calling it mixed. That is what I mean by Nash equilibrium. Okay, Nash equilibrium means when we are allowed to play mixed strategies. So we're just condensing all the information in A with the notation or with the understanding that this is the payoff of the first player. If we want the payoff of second player, we just negate the entries. Okay. So now let's talk about mixed strategy. Right? What do we know? A mixed strategy is a probability distribution. So let's say mixed strategy for first player. Do you want to name the first players? Alice and Bob. So for Alice, the first mixed strategy is, it's the probability distribution on how many elements? This is the number of strategies possible, remember. Probability distribution on S1, right? So that means I can describe it by a vector like this, such that right? This is my description of a mixed strategy. I can similarly write mixed strategy of Bob, which is going to be a probability distribution over n elements. That means it's a vector in such that each entry is positive Good. So we have described what a mixed strategy is. The first question is, suppose Alice plays X, Bob plays G, a deterministic strategy. Question is clear? And again, payoff now will always be in terms of Alice's payoff. Right? So what is, now we can talk about payoff in the game. My understanding, Alice's payoff is positive, whatever I am talking about. If I want to take, what is J transpose? Bob plays J means J is a deterministic strategy, right? It's one of the strategies out of these n. So I'm simplifying. Summation right. So this is saying that I am picking the jth column of A, right? Jth column is, this is a nice notation to denote jth column of A, right? Star means I can put anything here, J entry remains fixed. So the payoff okay. On the other hand, if Bob plays Y and Alice plays I, so Alice's payoffs, when Alice is playing I, it is written in ith row of A, right? Whatever happens when Alice plays I am just restricting to look at the ith row of A. And then each of these are played with this probability. So this is summation this is questions about this. that depends on, oh, the row I am considering it as a column vector. You write it as this way or this way. I can,
No, A is n cross n,
right?
and Y is n cross 1.
See, this is going to be n dimension. That the transpose depends on whether I am writing it like this or I am writing it like this. Right?
X is like a vector, or it is a strategy, right? X is a strategy.
It's a mixed strategy.
No, it is a mixed strategy. Okay.
Let's six 4. Okay, and now if let's say y is saying 1 by 3, 2 by 3, and Alice plays 1, strategy 1.
Okay, know for sure that.
Yes, this I is a deterministic strategy, right?
Okay.
That is why J I am using different letters just to say that, oh, this is a deterministic strategy. Then we will do the hard part also, but I wanted to start with this, right? So if this is the case, what is the payoff? Tell me. If Bob is playing this, Alice is playing this, what is the payoff? 1 by 3 times 1, 2 by 3 times 2. Whatever it is. Right? This is what we want to do. We want to take this row, weigh it with respect to the probabilities. Questions? If this is not clear, ask now, because things are going to get more complicated. So this might be, if you have seen it before, this might be easy. If you are getting stuck here, clarify. I am here not asking the payoff of Bob. I am only asking, I am now always asking payoff of Alice. Define it as payoff of game. Payoff of game is what Alice gets, what Bob has to give. Okay, so then there is no confusion. Okay. Then it is okay, right? Good. Now the next question is, what if Alice plays with X, Bob plays with Y? What is the payoff?
X transpose A,
Why?
A, I, C, X, I, Y, Z.
You guess the form by looking at this.
No, at first I thought that there is a change specific.
Okay. See, what is happening? When will they get Aij payoff? With what probability will they get Aij payoff? So that means I want to calculate this quantity. These are the possible profiles, I comma j. For each of the profile, this is the payoff, this is the probability. So this is the total payoff. Questions? Right? And then this is equal to this. How do we prove this? Vector matrix multiplication, and I'm not going to do it. Okay? And this is, I think, a very useful form. This is called actually a quadratic form. X transpose AX. It's called a quadratic form, and this is tremendously useful, especially when you talk about spectral graph theory and quantum computing and all those things. So, okay, good. So now we know what expected payoff is, right? And remember, what was Nash equilibrium? No player has incentive to change strategy unilaterally. Right? So it might happen that both of us change strategy, then the payoffs can rise. But if I keep my strategy fixed, you change your strategy, you're only going to lose. This is the Nash equilibrium. This is unilateral. You don't want to, like both players, obviously both players change, then it is very, very difficult. Equilibrium is when, okay, I'm going to play with this strategy. Now, whatever you do, this is the payoff I'm going to get. Okay? Sounds good? So, that means if let's say x naught y naught is a Nash equilibrium, right? Then I know this is the payoff for the first player, correct? Now this min. Because if at y naught this is not minimum, then second player has the incentive to change the strategy from y naught to y.
What is the player trying to do? Minimize payoff or maximize?
Second player is minimizing the payoff, right? Second player wants to minimize the payoff, first player tries to maximize the payoff. Let me just write it because, yeah, once you think about it, it's obvious, but yeah. First player wants to maximize right. Similarly, this is also equal to if not, first player will change strategy from x naught to x. So this kind of formulation is nice, but now let's intuitively see what Alice and Bob actually want, right? For example, okay, what does the first player want to do? Okay, Alice wants to maximize the payoff, right? So she wants to come up with an x, right, such that whatever Bob plays, she is not at loss, right? So she will assume that Bob plays the best possible for Bob and worst case possibility for Alice. So if Alice's strategy is X, what is the worst case for Alice? Assuming Alice has played X, what is the worst case?
X, Y, X naught.
Think about it.
Min of x transpose
Min over what?
y all
Right. So now, what is the worst case for Alice? Bob picks a y such that the payoff is minimized, right? So worst case is picks y payoff is minimized. Next. So Alice wants to come up with an x such that no matter what Bob plays, she is guaranteed at least this much payoff. Make sense? Now, similarly, what is going on in Bob's head? He wants to minimize his payoff such that whatever Alice pays, the payoff is maximum. Whatever pay, it is minimized by that y. So fix y. What is the worst case for Bob? Alice plays the max x. Oh, because, okay, the proof for zero sum is much simpler. And the case is I don't have to worry about A and B. For now, if I have to write Bob's strategy, it is going to be max over y, min over x, x transpose by, and then how am I going to relate these things? It depends on the relation between A and B. Okay, so there are different techniques. These are things are called fixed point theorems, which prove also strong duality, but using fixed point theorems you can prove. But that's a more general, more difficult task. In this case, these two quantities already look related, right? And surprise, surprise, von Neumann's minimax theorem basically says max x min y x transpose ay okay, and I'm going to answer every question about it except why is it not called Maximin theorem and Minimax theorem. Okay, von Neumann's Minimax is just for this particular thing. There are different versions of Minimax when this thing is not really linear, it's more complicated, but science Minimax and you can study. So this happened in 1940s. After that, Minimax in itself is a different branch. Okay. Good. So we have seen two ways in which players can possibly play. One is this abstract notion of saying, oh, probably there exists a point where both of them are happy. They know that other player is not going to change. That's the best strategy for them. This is one. We have done the other way where we are saying that, you know, what does Alice want to do? What does Bob want to do? And then von Neumann's Minimax theorem tells us that these two quantities are equal. There is some x naught, y naught such that x transpose this is also equal to A. Okay. Now, there is a small thing which I have put under the rug. I have not told you, okay, this is the optimization over x naught. This is the optimization over y naught, right? So, what is x naught? X naught is the x which maximizes this. Y naught is the y which minimizes this quantity. Is that y naught is the same which is going to minimize this quantity? It's not clear. It's an exercise, you can show it. It is true. The way it is set, right? You can show, so you can show that this indeed the y which will minimize this will actually be y naught. Otherwise, there is a contradiction. Okay, and it's just simply saying, oh, suppose there is some other y. Then you just compare it with x naught transpose a y naught, and then you will get something like this. So suppose x is the solution here and y is the solution here. So you can get this inequalities, but you know that these two are equal. This is Minimax theorem. So then y naught has to be, not has to be y, but this value is going to be same as this. Okay, but yes, I am not going to the detail because I want you to do it. It's not difficult. Okay, so that means von Neumann's Minimax, the intuitive approach of solving things, is giving us x naught, y naught. It's not necessary that y naught is the only y naught which minimizes this. Okay, and actually you can kind of show that there will be a deterministic strategy which minimizes this. I will come to that point. And if there are multiple deterministic strategies, any linear combination of them will also minimize this. So definitely it is not unique. The point is y naught definitely is one of the minimizers. No, x and y are strategies now, right? This is the, oh.
Only for strategies. So
It is only for strategies, yes. This is, okay, this is a mixed strategy. Sorry, I probably, if I want to write it as a theorem, I should clarify. A is an M cross N matrix, X is a probability distribution over M elements, Y is a probability distribution over N elements. Then I look at this quantity, this is equal to this. This is what I'm saying. Okay? Yeah, you can't take arbitrary vectors X and Y. See, generally you need to have a normalization, because otherwise min-max doesn't make sense. You just multiply by something, it can go to infinity, right? So clearly you have to have some kind of a normalization, you have to have a bounded region. And then you want positive in this case. So what I'm saying is that positive is the only extra constraint in some sense which I'm putting. You need some kind of a normalization anyway.
So if it was a bounded MX, then also?
No. What I'm saying is that, yeah, so if you want to make sense of this statement, you should optimize over a bounded set. Now, for one dimensional min-max, it works when that bounded set is of this kind. I'm not saying it works for every convex region, no. But there are generalizations of this, no. I'm not saying this is the only one which works.